Imagine a standard subway commute. It's a Tuesday morning, the lighting is dull, and the train car looks exactly like it did on Monday. Your brain is highly efficient, so it automatically discards about 99.9% of this entire experience. But then you look across the aisle, and someone is sitting there wearing a brightly colored clown hat. You'll remember this specific moment at dinner tonight, and you will likely still remember it 3 decades from now. We tend to think of our memory like a smartphone camera, where you see the clown, hit record, and save a digital file to a hard drive. In reality, forming a permanent memory is a biological construction project. That image of the clown must survive a brutal, multi-stage obstacle course, where weak connections are ruthlessly pruned away. Converting a fleeting observation into a lasting physical record requires a strict physiological sequence. Scientists call this process memory consolidation. Within minutes of spotting Rat Clown, your brain begins work on a microscopic level. It triggers early genes that instruct your cells to synthesize fresh proteins, the physical building blocks used to bridge the gaps between nerve endings. These initial connections are fragile. For the memory to survive past the 3-hour mark, late genes must activate to produce a second wave of proteins that solidify this new architecture. Activating those late genes require 2 specific triggers. The first is emotional significance. Because the clown is bizarre, your amygdala flags the event as unusual and potentially critical for your future survival. The second trigger is repetition, or long-term potentiation. When you text a friend about the person on the train or replay the moment in your head during lunch, you force that neural circuit to fire again, physically thickening the connection. Without that emotional weight or active repetition, these structural proteins simply dissipate. The bridge collapses and the memory vanishes before the day is over. If the clown survives the day, the heavy lifting moves to the first night. During the deep, slow wave phase of your sleep cycle, the brain begins systemic consolidation. Here, the hippocampus acts as a biological printing press. It takes the neural trace of your day, the engram, and rhythmically shuttles that sequence back and forth to the outer layers of your cortex. We know how vital this structure is because of surgeries performed in the mid-20th century. Doctors attempting to cure severe epilepsy occasionally removed the patient's hippocampus entirely. While the operations stopped the seizures, they also caused anterograde amnesia. These patients kept their old memories, but lost the ability to save new information for longer than a few minutes. This biology is why cramming for an exam rarely works. The hippocampus becomes overloaded. It requires waking breaks to process data and multiple nights of sleep to effectively sync those connections with the cortex. During these hours, your brain functions as an active construction site, hammering short-term data into long-term biological architecture. Months later, the memory of the clown shifts. The episodic details, the specific smell of the train or your exact seat, gradually fade. What remains is the semantic memory, the pure, context-free facts. In this final stage, specialized glial cells wrap the established neural axons in a thick insulating sheath called myelin. This coating acts like insulation on a wire, accelerating the nerve impulse and making the circuit resistant to decay. This physical hardening is the foundation of professional expertise and memories that last a lifetime. This final, physical hardening of your brain's circuitry over a long horizon is what provides the durability needed for lifelong memories and professional mastery. When you sit down to learn a new skill or retain crucial information, you are operating within these physical constraints. Success in learning is never a matter of sheer willpower. To make data stick, you must provide the raw materials your biology requires: emotional engagement, repetitive firing, daytime breaks, and deep sleep. While these memories form the basis of our past, they depend entirely on this hidden and highly vulnerable biological sequence. We experience our lives in the waking light, but the memories that make us who we are physically built in the dark.